Welcome to this explainer. Today we're diving into something absolutely fascinating. We're going to see how the super basic rules of work and energy, concepts you probably associate with pushing blocks or throwing a ball, seamlessly translate into the incredibly complex world of fluid mechanics. By the time we're done here, you'll see that whether it's a massive airplane soaring through the sky or the blood pumping through your own veins, it's all governed by the exact same elegant laws of energy.
Here's our roadmap for today. We'll start with the power of energy, look at efficiency and wasted work, and then plunge right into the fluid world. From there, we'll tackle drag and terminal velocity, the rules of fluid flow, and wrap it all up with energy conservation in fluids. Let's get right into it.
All right, Section 1, the power of energy. To make sense of the complex stuff later, we've got to ground ourselves in the absolute basics of motion, work, and energy. Let's kick things off with kinetic energy. Put simply, it's the energy an object has just because it's moving. A sliding block of wood, a speeding car, a planet orbiting a star. If it's moving, it's got kinetic energy. Now, if we want to really understand a physical quantity in physics, we have to look at its units. Kinetic energy is measured in joules. But a joule isn't just some random word, it's a derived unit. It's a really elegant mashup of basic base units, mass in kilograms multiplied by velocity squared. So that's kilograms times meters squared per second squared. Grasping these fundamental dimensions is going to be our secret weapon today. But hey, how does an object actually get that energy in the first place?
Well, think about a cricket player striking a ball with a bat. They're applying a force. And applying that force over a certain distance, that's what physics calls doing work. Here's where looking at the dimensions is just pure magic. Work is force, measured in newtons, times distance, measured in meters, Newton meters. And guess what? If you break that down, it has the exact same base unit dimension as the joule. This dimensional proof is awesome because it shows exactly why work and energy are perfectly interchangeable. The work you do doesn't just vanish. It literally transfers right into the object, giving it that kinetic energy we just talked about. Work is the action, and kinetic energy is the payoff.
Moving right along to Section 2, efficiency and wasted work. Because, as we all know, we definitely do not live in a perfect universe. While total energy is always strictly conserved in a closed system, in the real world, a ton of the useful work we try to do gets lost to non-conservative forces, like friction. Take an electric generator. It's incredibly impressive, clocking in at around 98% efficiency. But look further down the scale at a standard automobile engine. It operates at only about 25% efficiency. It's literally wasting 75% of its fuel energy, transforming it mostly into useless heat instead of the actual work of moving your car forward. What's really cool about efficiency is that it's a dimensionless physical quantity. It's just a ratio, joules out divided by joules in, meaning the units cancel each other out completely. The big pro of a dimensionless number is that it lets us universally compare totally different machines, from power plant generators to car engines. The downside, though, is it tells us absolutely nothing about the actual scale or power of the machine, just its ratio of waste. So here's the big question. We know exactly how energy, work, and non-conservative forces like friction behave with solid objects sliding or rolling around. But what happens when the thing in motion isn't a solid block at all? How do these exact same rules hold up in a fluid, like water or air? That brings us to Section 3, entering the fluid world. This is a realm where liquids and gases play by their own fascinating variations of the rules.
Just like solid blocks push against each other, fluids exert forces too. Drop an object in water, and the fluid pushes back with a net upward force called upthrust, or buoyancy. It's all governed by Archimedes' principle, which basically says this upward push is exactly equal to the weight of the fluid that gets displaced. And remember, whether a bat is hitting a ball or water is holding up a ship, this force is always measured in that derived unit, the Newton. This single, elegant rule explains why massively heavy steel ships can float safely on the ocean. They're shaped to displace a massive amount of water. It's the exact same reason a helium balloon floats up into the sky. It's simply displacing air that's heavier than itself.
Section 4, drag and terminal velocity. Because fluids don't just push things up, they also push back against motion. When objects move through fluids, they hit resistance. In liquids, we call it viscosity. In gases, it's viscous drag. Think of it as the fluid version of friction. Check out this velocity graph of a falling paratrooper. When they jump out of the plane, gravity pulls them down, and their downward velocity rapidly spikes. But air resistance acts as a non-conservative drag force pushing back up against them. The faster they fall, the stronger that drag gets. Eventually, you hit terminal velocity.
the exact moment the downward pull of gravity perfectly balances the upward push of drag. Right then, their net acceleration, measured in meters per second squared, drops to 0, and their velocity locks into a constant rate. When they deploy the parachute, bam! That massive surface area creates a huge spike in drag, rapidly slowing them right down to a new, much safer terminal velocity for landing.
All right, Section 5, the rules of fluid flow. Up to now, we've talked about solid objects moving through fluids. Now let's look at what happens when the fluid itself is the thing moving. Fluid dynamics can be ridiculously complicated, so physicists use some brilliant models to simplify things. First, we have to classify the flow. Look at the visual chaos of the turbulent flow on the right and compare it to the smooth, orderly, streamlined flow on the left. In streamline, or laminar flow, every single particle perfectly follows the path of the one right in front of it. It's orderly and predictable. Since real-world turbulent flow is a mathematical nightmare to calculate, we usually rely on ideal streamlined flow to make our calculations possible.
Assuming we have that perfect, ideal flow, some pretty amazing rules pop out. Think about watering your garden. When you thumb the end of the hose, you're shrinking the cross-sectional area of the opening. But since liquids are largely incompressible, the exact same volume of water still has to squeeze out of that hose every single second. To pull that off through a smaller hole, the water simply has to speed up. The dimensions tell the whole story here. Area is square meters, and velocity is meters per second. Multiply them together, and you get cubic meters per second. That derived unit is the volume flow rate. It mathematically proves why squeezing a hose speeds up the water. The volume per second literally cannot change.
Which brings us to Section 6, Energy Conservation in Fluids. This is the climax of our explainer.
Here's the big reveal. The complex equations of fluid mechanics are actually just our old buddies, work and energy, wearing a clever disguise. Take a look at this fluid flowing through a pipe that changes both its width and its height. As the fluid gets pushed from the wider, lower section up into the narrower, higher section, work is actively being done by the fluid's pressure pushing it along. Pressure is just force spread over an area, measured in the derived unit of pascals, or newtons per square meter. And just like swinging that cricket bat, the work doesn't disappear. The work done by the pressure transforms directly into the fluid's kinetic energy as it speeds up in the narrow pipe, and its potential energy as it fights gravity to get higher.
And this right here illustrates where one of the most famous equations in physics comes from. Bernoulli's equation can look completely intimidating in a textbook with all its variables for pressure, density, velocity, and height, but look at these 3 simple steps. It is literally just the work-energy theorem we talked about at the very beginning. You calculate the work done by pressure, equate it to the change in kinetic and potential energy, shuffle the terms around, and boom, you've got Bernoulli's equation. And the ultimate proof that it's just energy conservation? Dimensional analysis. If you break down the units for pressure, kinetic energy, and potential energy in this equation, every single one simplifies to the exact same base units, energy per unit volume, or joules per cubic meter. The physics is perfectly balanced.
The law of conservation of energy forms the basis of Bernoulli's equation. I honestly love this quote from our source material because it sums up our whole journey beautifully. Whether you're trying to figure out the wasted efficiency of a mechanical car engine, predicting the aerodynamic lift that keeps a jumbo jet in the sky, or designing a city's water supply, the universal law of conservation of energy is the skeleton key to understanding it all. The rules never changed at all, they just adapted to their environment.
And that leaves us with a pretty wild thought to take away. As we've learned today, even the highly complex flow of blood pumping through the varying arteries in our own bodies is dictated by these fundamental equations of continuous flow and energy. It really makes you wonder, if the deepest mechanics of life itself are dictated by these super simple energy rules, what other grand mysteries of the universe are just waiting to be unlocked by zooming out and simply following the flow of energy? Thanks for joining me on this explainer, and keep questioning the mechanics of the world around you.